start again with the Lamport's algorithm for distributed mutual exclusion, and then we will see that there are certain improvements that we can do over that algorithm. Now, let us recall that what the algorithm does, that when a process Pi wants to enter the critical section, then the process sends out request messages, right. When the other processes receive that, they send reply messages, then the critical section execution takes place, and after that is done, then the process sends out release messages. Now, recall that the reason that we had these reply messages was that Pi needs to know that there is no other request which has a smaller timestamp than its own request, which is in transit. Okay. Now, there can be no such request having a smaller timestamp in transit, because messages are delivered in FIFO. Right. Now, one simple improvement that we can have here is that consider Pj. Suppose Pj had a Pj has a request. Let me start afresh in another sheet. Suppose at a point of time the request of Pi reaches Pj, right, and let us say that this has some timestamp TSI I. Okay. Let us say that Pj has also sent out a request. So, this is Pi's request. Let us say that Pj has also sent out a request, another request, and this has timestamp TSJ j, right. Suppose TSJ j is greater than TSI I. Okay. Then PSJ does not have to send a reply to this. Let us understand why. In this case, what I am saying is that then Pj does not have to send reply to the request TSI I. Why? Right. That is because all that Pi needs to enter the critical section is some message from J which has a timestamp greater than TSI I. Right. So, this request itself is a message which has timestamp greater than TSI I. So, there is no need to send another reply message. When it receives this one, no, it receives this TSII. When it receives this request message, it compares TSII with TSJJ and finds that TSJJ is greater than TSII. So, here that reply which it is normally supposed to send, that it will not send. See, at this point of time it has the request TSII because that is time stamped on this, right. The message has this timestamp and TSJJ is this timestamp. Now, it knows that I have already sent a message having higher timestamp to I. So, why send the reply again? Okay. So, it will not send the reply, right. So, this is a simple improvement over Lamport's algorithm in which we save some messages. See, this is a very specific case. The specific case is that when I receive a request from PI, at that time PJ has already made a request having a higher timestamp. So, under that circumstance the reply need not be sent. Okay. That is one kind of optimization. Then we will see another optimization which is more significant, and that is called the Ricart-Agrawala algorithm. In this algorithm, this is what we are going to do. We are going to we will do away with the release messages. How? So, let us understand how we are going to do away with the release messages. So, consider this situation that PI has made a request TSI I, okay, and it has sent the request message to PJ, right. Now, PJ sees that it has in its queue some request TSJ J, right, and it sees that TSJJ, that TSJJ is less than TSI I. So, its own request is smaller than that of the request that it has received from I. Now, let us understand the way in which Lamport's algorithm works. In Lamport's algorithm, PI will not be able to enter the critical section until PJ has completed, right. So, even if a reply message is sent here, PI will still not be able to enter. Why? Because this TSJJ will reach PI somewhere, and then PI will know that there is a pending request having smaller timestamp than its own. So, in Lamport's algorithm what will happen is that this request will reach PI, then this reply will come here, this is the reply. In the meantime, PI will enter the critical section, it will execute the critical section, and then it will send out a release message. When this release message is received, at that time PI will be able to enter the critical section, right. So, PI will enter CS somewhere here, right. Now, what we want to say here is there is no need to send this reply message here. We could instead do the following thing, that do not send the reply message here, because you know that even if you send a reply, PI will not be able to enter the critical section until the release is sent, right. So, withhold the reply message, and instead of sending a release here, send the reply here after you are done. Okay. So, what does the reply message say? The reply message says that J is giving permission to PI to enter the critical section. As long as it has a request having smaller timestamp, it will not give I the permission. Once it is done with executing this critical section, then it will give the reply message, right. So, what we are doing is, instead of giving release messages, we are merging the reply and release messages into only one form of message called the reply message, right. So, any node which has a lower timestamp request in its queue will withhold the reply, it will do the critical section and then give the reply, right. And we know that until that reply message is received by the other process, it will not enter the critical section, right. We have to prove that it will not start, right. So, we will prove those things one by one. So, let us look at the algorithm now. This is called the Ricart-Agrawala algorithm. This is an improvement over Lamport's algorithm. The main idea is that node J need not send a reply to node I if J has a request with timestamp lower than the request of I, since I cannot enter before J anyway in this case, right. Now, this is an important thing. This algorithm does not require FIFO channels, okay. It does not require FIFO channels. So, a node will enter the critical section when it has got reply messages from all other nodes, okay. At any point of time, if there is any other node which has a smaller timestamped request, then that node will not reply, okay. So, the other nodes will not be able to enter the critical section. The algorithm will not starve, because at any point of time there is always one node which holds the minimum timestamp request, right. So, when that node sends out its request, all other nodes will reply back, right. Is that clear? Because you see, we are making it mandatory for every node to receive all the reply messages, right. So, whenever it gets the reply messages, then it can enter the critical section. So, it is like taking permission from everybody else. The algorithm says that, okay, if I want to enter the critical section, I need the permission of all other nodes to enter the critical section. Now, when is a node going to give me permission? If it does not have a lower timestamp request, okay. If it does not have a lower timestamp request now, it can never have a lower timestamp request in the future. Why? Because we are using Lamport's clock. So, whenever you get a request, your clock value becomes at least as large as the value of that request, right. So, if at a point of time you get a request and you do not have any request having smaller timestamp, then you will have to give him the reply, right. Now, think of the whole distributed system. Among all the requests, there is at one request which has the smallest timestamp, because timestamps are totally ordered. Totally ordered, why? Because we are appending Lamport's clock with the process ID. So, it is totally ordered. So, there is some site which holds the minimum timestamped request. Now, all other nodes will have to give this node the reply. So, it will get all the reply, it will enter the critical section, right, and this node is withholding the reply for all the other nodes, because it has the minimum timestamped request. So, it has not replied to anybody else, right. Now, think of the node which has the second smallest timestamp. It has got reply from everybody except the smallest one, right. When this one completes the critical section, it will send the reply messages to all the other nodes, right, whoever has requested, and then the one which has the second smallest timestamp will get the only remaining reply, and that will then enter the critical section. Okay. This is how the algorithm will continue. Is it clear? Dipankar? Anvesh? Okay. So, what is the number of messages per critical section invocation? 2n minus 1. So, that is a improvement over Lamport's, because Lamport's needed 3n minus 1 messages per critical section invocation, because we had n request, n reply and n release messages. Now, we only have the request and the reply messages, there is no release messages.
But sir, it can be greater, because that special case we have considered. In that case it was the 2 messages only, but if there won't be any timestamp, then send acknowledgement and then again it will.
No, all messages are time stamped. What makes you think that they are not time stamped?
No, I mean that is special case we have considered that they have to also the request we have sent, and that process also wants to enter the critical section. What happens if it doesn't want to?
If all of the nodes don't have a request with a lower timestamp, then they will all give a
Reply.
And then again it will go to release message.
No, I didn't get your question. Can you repeat the question? We start. Yeah. First, please repeat the question. Then you do that. Yeah. So you are saying that PI makes a request to PJ and PK. Is that what you are saying? Okay. So PI makes a request to PJ and PK. Then
PJ will send acknowledgement to.
PJ will send a reply, provided that PJ does not have a lower timestamp request. Yes. Yes. So then PJ will send a reply. Yes. Right. Then after PI completes the critical section operation, no, there are no release messages here. There is only request and reply. There is no release message.
But then the other processes probably will think that it's still going under critical section.
No, they won't. If there is any other process which has made a request, okay, suppose there is another process PK which has made a request here. So it has sent the request messages, right. Now PI will not respond to this request message until it is through with its critical section, right. This is where it will send the reply. Now when you get a reply from PI, PK knows that PI is not in the critical section, neither does it have a request with a smaller timestamp than PK. Right. So it knows it can enter. When a node is giving you permission to enter the critical section, it is implicit in that permission or in that reply message that the node is not contending to enter the critical section as of now. It may have a higher timestamp request, but it certainly does not have a lower timestamp request than the one of PK. Okay, that is what the reply message indicates. Is that clear? So, what is the synchronization delay again between one process exiting the critical section and the next one entering the critical section? One reply message. Why is that the case? Because as I mentioned before, the process which has the second smallest timestamp request will get reply messages from all processes except the one which has the minimum timestamp. Only the minimum timestamp one will not respond to it, right. So, the one which has the minimum timestamp request will complete its critical section and then reply to the request of the second smallest timestamped one, right. And when it replies to the second smallest timestamped one, then the second smallest timestamp one will get all replies because it has already got it from the remaining ones, only this one was pending, it will get this one and immediately enter the critical section, right. So, the delay, the synchronization delay between process Pi completing the critical section and the process Pj entering the critical section is the transmission delay of the reply message, right. So, it is again transmission, the synchronization delay is the same as Lamport's. Requests are granted in order of increasing timestamps, right. That also is clear, I think, because at any point of time only the process having the minimum timestamps is getting reply from everybody. No, synchronization delay is the delay between the completion of critical section of one process and the entering of the critical section of the next process. That is the definition of synchronization delay. All right. Now, we will look at another improvement of this algorithm. To understand this, we first again let us reiterate what is happening here. When a process wants to enter the critical section, it asks the permission of all the other processes. The reply messages are those permissions. When it gets permissions from all other processes, it enters the critical section, right. Nodes which have smaller timestamp requests do not permit the nodes having higher timestamps request by not giving the reply message before it is done, right. This is the way that Ricart-Agrawala's algorithm works. Now, observe that if I am Pi, you are Pj, you have given me permission to enter critical section. So, you have sent me a reply message. That means, you do not have any request which has a smaller timestamp than my request, right. Now, when I am done, when I have your reply, okay, then can I enter the critical section again without taking fresh permission from you? Yeah, see, this is the important thing to understand. You have given me permission to enter the critical section, right. If you have made any request after that and I have not replied to that, then you cannot enter the critical section, right. Then I can again enter the critical section, right. So, what does this mean? It means that if at any point of time I have received a reply from you, but I have not given you a reply after that, then I do not need your permission to enter the critical section again, right. Why is this useful? Because you gave me a reply, I used that reply, I entered the critical section, I did my job. After coming out of the critical section, I see that I need to enter the critical section again, but I have not received any request from you. Now, since I have not received any request from you, I see no reason why I should take your permission again, because as far as your status is concerned, you have given me the permission to enter the critical section and thereafter you have not made a request to me to enter the critical section, right. And I know that until I send a reply to you, you cannot enter the critical section. Then I know that because I have not sent a reply to you, there is no way you can enter the critical section at this point of time. So, there is no point again sending you a request and getting a reply from you. Instead, I can directly enter the critical section, right.
Only those nodes which are not send the request between.
Only those nodes which have. So, let's now formalize this thing. Okay. This is the okay. We have already done this. This is the Ricart-Agrawala algorithm. Now, this is what is the improvement. This is called Ricart-Carvalho algorithm. The main idea is once I has received a reply from J, it does not need to send a request to J again, unless it sends a reply to J in response to a request from J. Okay. Now, what is the message complexity per critical section invocation? It can even be 0. It can even be 0. When will it be 0? When after coming out of the critical section, you see that there is no other pending request from anybody else and you want to enter the critical section again. You already have permission from all the other nodes. So, just go ahead and enter the critical section without any further messages, right.
Sir, if there is another node which J also has given me a request earlier, and J also wanted to enter critical section, and now after I finishes critical section, it again wants to enter into critical section.
Yeah. So, let me draw the situation. Requests were sent out, replies were received, right. Then this one entered the critical section. Now, you are saying that this there is a request from J also, okay, which is received somewhere. Okay, this is a request from J. Now, when this request is received, suppose this timestamp on this is TSJ J, right. When this is received, according to Ricart-Agrawala, what will PI do? PI will see, does it have any request of smaller timestamp after the execution of the critical section? No, right. So, it will have to send a reply. Okay. Now, the moment it sends the reply, it cannot enter the critical section until it gets a reply back from PI. See, here it has passed on the permission to PJ. Until it gets the permission back, it cannot enter the critical section again. Only if there were no pending requests, then it can again enter the critical section.
Sir, actually it can enter, but that will not be good. You want to say that?
I mean, it can enter, but then you will not be executing critical sections in the order of increasing timestamps, which would be unfair, right.
Sir, even if you don't do that, still you can't guarantee that you are executing it in order of timestamps, because the request from J might be might not have reached it, but
Yes.
J has already sent the request.
That is a good question. Let me draw that situation. The situation that I believe you are referring to is like this, that PI makes a request,
Hello.
PI gets the reply, enters the critical section, right. Now there is a request here TSJJ which is sent out here but reaches much later, right. Now at this point of time this one makes a request with TSI I, right. It has made a request with TSI I and TSI I is less than TSJJ, sorry, greater than, right. And you use this to enter, use the fact that you already have a reply from PJ to enter the critical section again here. This is the question that you are asking, right. Now this is possible provided that this is updated in a way that this can exceed TSJJ, right. Now how can that happen? That can happen actually, because in Lamport's clock these two events, this request and this request, they are not causally ordered, right. So in the total order this is that these are turning out to be in the opposite way, that it should have done this and then this, but you think of one thing, that these two are actually two concurrent requests, there is no causal order between them, right. So in that sense it is doing it in the order of this, because we just annotated the process IDs and made them into a total order. That is why it looks like we are executing them out of order, but actually these two are concurrent events. Right. Had they been causally ordered, that would have happened if, for example, this got this message and then started executing this, that would have been a out of order execution, which is not permitted by any of these algorithms, right. But if they are concurrent events, they can get executed in arbitrary order, and it may violate that thing that the smaller one is getting executed after the larger one, because we are imposing a total order by annotating it with process ID.
But you can't use this particular algorithm again in a bank transaction, because if one bank updates a particular account, they have to be causally ordered. The transactions have to be. This particular algorithm may not work.
No. There is nothing bad about this. See, all that is happening here is, it appears to you that there is a smaller timestamp request which is getting access to the critical section after a request with higher timestamp gets access to that, right. Then that is a lack of fairness, but there is no lack of correctness, like there is no starvation, there is no breakage of the mutual exclusion requirement. So from those points of view, this is a sound and correct algorithm.
But so point was that what are you doing exactly in the critical section?
In the critical section, that's a very you are doing something which you don't want to do. You are updating some data items maybe, which you want to lock and do. You don't want some other process to work on the same data item at the same time. Okay. So critical section, typically in the critical section you access data or data structures in a atomic way, that until you are completing your transaction, no one else will be able to access that part of the data structure. That is what we typically want to do with critical section. Now critical section, again people look at it in two ways. One is that there is a part of the code of your program which you would say this is my critical section, and no two processes will be in this part of the code at the same time. Right? Now that's another way of looking at it. Essentially, it's some part of the data that you are manipulating there, which you don't want to have too many processes or more than one process working on the same data at the same time, because then that might lead to a consistency problem. So what exactly is being done in the critical section depends on the application. Our job is to give it access to the critical section. Okay. So is this improvement over Ricart-Agrawala clear, that you can enter the critical section again without taking permission of other. Right. Now in all the algorithms that we have studied so far, we have been only working with taking permission from all other processes. So whenever one process wants to enter the critical section, it has to take the permission from all the other processes. Right? Now we will see one algorithm where you don't need to take a permission from all processes, but you need to take a permission from only a subset of the processes. So this is called Maekawa's algorithm. Permission is obtained from only a subset of other processes called the request set or the quorum. For each process I, we have a request set Ri. Okay? And the requirements are that for all ij, Ri intersection Rj is non-empty. Okay? Why do we have this requirement? Let us understand this first. We want that whenever a process wants to enter the critical section, it will have to take permission from every member in its request set. What is a request set? Request set is a set of processes, subset of the processes. Okay? So for process 1, process 1 has to take permission from these processes. Process 2 has to take permission from these processes. Okay? So process I takes permissions from the processes belonging to the set Ri. Right? Now when you get permission from all the processes in your request set, you enter the critical section. Right? Now consider two processes Pi and Pj. Their request set must have an overlap. Why? Because the process which is common in both the request sets Ri and Rj will arbitrate between Pi and Pj. That process which is in the intersection of Ri and Rj will determine that at this point of time whether Pi is in critical section or Pj is in critical section. If for two processes their request sets are disjoint, then Pi can take permission from the ones in its request set. They don't know about Pj's status. Pj can take permission from its own request set and both can enter critical section at the same time. If there is an intersection, then there is at least one who knows that Pi has requested and Pj has requested, and it will permit at a time only one of them. So either Pi will enter or Pj will enter. Right? So between every pair of processes there has to be one node which arbitrates, one or more, right, and gives permission to only one of them. Okay, that's the reason that we want that for all ij, Ri intersection Rj has to be non-empty. For all I belongs to Ri. So process Pi must necessarily belong to its own request set. Okay? And these two are the necessary requirements, and these two are for performance. for performance we want that the size of all the request sets are the same. Okay, so sigma the size of Ri is k. Okay, and any node is contained in exactly d request sets for some d. Why? We want that the overhead of every node in arbitrating requests is the same. So, if you are in d request sets, then you are responsible for giving permissions to d nodes. Right? So, we want that every node, that this d is a constant for all nodes. So, every node is a member of a fixed number of request sets, and that fixed number is d. In Maekawa's algorithm, we have k equal to d equal to root n. Right? So, the number of nodes in every request set is k, every node is in k request sets, and the value of k is root of n. Okay. Now, there is an methodology by which you can take a network and then distribute the nodes of the network into root n number of sets such that every node belongs to only root n number of sets. Number of sets, request sets, the size of the request sets will be root n, and each node will belong to exactly root n number of sets. Is that clear?
That means critical section is not same for all the nodes. Like when the intersection is it is null, that means there are two sets of processes, but they don't share the same critical section.
No, critical section is the same for all of them, and there is it cannot be null. You see, Ri intersection Rj is not equal to null. So, for every pair of request sets there has to be an overlap, right. So, let me explain what we mean by this.
Sir,
we are
what is the criteria to select this subset for a particular I and j?
There is no particular criteria. The only thing that we want to make sure is that every node will have to take permission from root n number of other nodes, and every node will participate in the arbitration of root n number of processes. So, what does it mean? That we are partitioning the nodes of the network into root n number of sets. So, I have R1, R2 and like that up to R n. This is a request set. Each request set, the number of nodes that it has is root n, right. Number of nodes that it has is root n, and every node, now every node is going to belong to number of request sets. So, it belongs to root n number of request sets. Okay. How we obtain these sets is a different issue which we are not going to discuss, at least not in this lecture, right. But we are given these request sets. We are given that for each process I there is a request set Ri, and the request sets satisfy the requirement that for any Ri and Rj, intersection of Ri and Rj is not null, and the size of Ri is root n, and every node is a member of root n number of request sets. Okay. Now, given that that is the case, what the algorithm will do is that we will take permission from each member. A process Pi will take permission from each member of its request set, right. when it gets permission from all members of its request set, it will enter critical section. Mutual exclusion is automatically guaranteed. Why? Because assume that two processes Pi and Pj are in the critical section at the same time. Pi and Pj are in CS together. We will show that this cannot happen. Why can't it happen? Because Ri and Rj have some common node. Let us call this node Pk, right. Now at a given point of time, Pk will not reply to both Pi and Pj. It will either reply to Pi or it will reply to Pj. It will not reply to both of them, right. So once it replies to Pi, Pi can enter the critical section, do its work. When it releases it, then it will respond to Pj. So that guarantees that Pi and Pj can never be in the critical section together.
Okay. Every request set will have a node from every other request set. It needs to have.
Every request set will have a node.
At least one node from every other request
Yes,
set.
yes, because the intersection between every pair of request sets is non-empty. Right? We are going to come. Actually, we will need more because there will be another problem which I am going to describe. May not be in today's class, but in the later class. Okay, so let us see the algorithm pseudocode. To request critical section, I sends request message to all processes in Ri. On receiving a request message, send a reply message if no reply message has been received, has been sent since the last release message is received. Okay. So now when a process receives a request message, see the thing here, it will send a reply message if no reply message has been sent since the last release message is received. So if a reply has been sent and the release has not been received, that means that this process has given permission to somebody to execute critical section. It cannot simultaneously give permission to another process, right. So only when the release message comes back, then it can again send a reply to this. Update status to indicate that a reply has been sent, otherwise queue up the request. Okay. To enter critical section, I enters critical section after receiving reply from all nodes in Ri. To release the critical section, send release message to all nodes in Ri, because it had taken permission from all nodes in Ri. So all nodes in Ri must know that it is out. Now on receiving a release message, what will a process do? It will send reply to the next node in its queue and delete the node from the queue. If queue is empty, update status to indicate no reply message has been sent. Right. Now this algorithm obviously has fewer number of messages because it has to take permission from a smaller subset of the processes, unlike the previous ones where you have to take permission from all nodes in the network, right. But this has the problem of deadlock. We will show in the next class that this algorithm can lead to the processes getting deadlocked, right. Then we will talk about the ways of getting around the deadlock problem, right. So that will happen in the next class.